We're not going to work. You were working. Come on, buddy. Ta-da. Try the other color. Are we going to work? Man, this is the first day. The best thing is I just started recording this, so. Okay. You were literally just working. Okay. Otherwise, we'll swap it. Hey, there you go. Okay. Cool. Working. Okay. So, just wanted to start a little bit about myself. As I said, my name is Professor Christians. This is my family. So we have 3 kids. Along the top on the top left is Graham, that's his like baseball face from this summer. I don't know. And then Clara, who's really scared of snakes and likes to scare her grandma. And then Elliot, who is on the beach reading Lego instructions. Because that's kind of how we roll. There's me and my wife Allie in the bottom, our blind 10-year-old dog Scout in the middle, and then Clara again eating ice cream, which was a pastime that we participated in quite a lot this summer. One of the nice things about Michigan. So I like engineering. I love talking about energy. That's one of my passions. That's one of the reasons I like thermodynamics. Is a lot of it is about how we convert one form of energy into another and how that process actually works. So that's one of the reasons I like this class a lot. I hope you will too. I think we get kind of in the weeds of a lot of stuff, but it connects to a lot of really interesting and important conversations. I love reading. I love hiking, running, biking. If you read any good books and want to pass them my way, I would love that. Do you have any good ones that you read over the summer? Maybe you guys don't read over the summer, but read books. They're good for you. Yeah. So that's a little bit about myself. I've been here at Hope for this is my 4th year. So not too much longer than most of you, but I guess a little bit. So again, I'm excited to be back here. I'm excited to be teaching this class. I hope it's going to be a good semester. So as I said, we'll kind of get into the syllabus-y type stuff in a little bit. But just to get a little bit of a sense of what we're here for and what thermodynamics is all about. Does anybody know who this person is. If you do, I guess you should probably just like leave the class, because I would imagine you don't. I certainly wouldn't have. You'll learn his last name. You don't need to actually learn anything cool about him. This is, well, you can see maybe by, so the title there is the title of a book that he wrote in 1824. And it's an important book in the life of thermodynamics, because this is really where starting to think clearly and rationally about how we turn one form of energy into another becomes more of a discipline rather than just like high school science experiments. Right? When we start to try to put laws and a framework and how do we think about this stuff instead of just kind of messing around in your backyard and seeing what works. So from the date, from the title of the book, what is this book kind of primarily thinking about, or what is he writing about? Yeah, Jacob. Steam engines, right? So this is where thermodynamics became a thing. Is when 1800s, the Industrial Revolution, people started to think, how can we use the motive power of fire? How can we turn heat from burning coal primarily? How can we turn that into motion? How can we do stuff interesting with it? How can we convert thermal energy into motion? This is still what we do. We convert thermal energy into motion. So this guy, his name is Nicholas Leonard said Carnot. Carnot is a name that will pop up. Not for a while yet, but in a few weeks, 4 or 5 weeks, we'll hear this name again. And just because I think it's always a little bit interesting. So he attended École Polytechnique, which is a French university, at 16. So we're all, I guess, a little bit behind the 8 ball, as it were. One of the profs that he had while he was there was named Ampere. Maybe you've heard of him. Right. One of the nice things about sciences back in the day is one, you had to be independently wealthy because no one would pay for you. But everything was undiscovered. So people like Ampere, right? Ampere's law is now discovered, so you can't find it again. Apologies. So he was at this university. He wrote the book. So you can see by the date, he was 27 when he wrote this book. And he wrote it while he was an Army engineer. So kind of this was like his night gig, I guess. I don't know how it worked. But then, of course, because it's 1800s, he died of cholera when he was 36. So there's a lot of new, interesting science to be discovered, but I wouldn't want to go back to the mid-1800s. So this is where thermodynamics came from. This is most certainly not where thermodynamics is today. I don't know, did anybody like drive to campus with a steam engine recently? No, probably not. Although you'll be surprised, all of the different places that thermodynamics is today. So this is a very thorough review that I did by searching thermodynamics on Wikipedia. I just think it's interesting and nice to get kind of a sense. We're gonna right. This is applied thermodynamics. We have a 2-credit, 1 semester course. We're gonna touch a little piece of what thermo is. It's all over the place, and there are lots of different interesting applications. Some that you might run into later in your career, no matter what field you might be interested in. Right. So just kind of a listing by date. So starting 1824, classical thermodynamics. So that's Carnot. First starting to put this framework about how do you turn one form of energy into another. And that's really what thermodynamics is. Thermo, heat, dynamics, movement. So it's how do you turn heat into movement, but it's really more broad. And we'll get to a little bit what that actually looks like. Just some interesting ones. Relativistic thermodynamics. How do you connect applications in thermodynamics to Einstein's theory of relativity. Biological evolution of thermodynamics. How can you connect some of the principles of thermodynamics entropy to evolution? Atmospheric thermodynamics. If you're looking at global climate change, you're looking at thermodynamics, how does that play out in the atmosphere? Earthquake thermodynamics, I think that's kind of a fun one. You typically don't think of like earthquakes and how we generate energy maybe as pretty different things, or earthquakes in a steam engine as pretty different things. But all of these things are connected by some of the same kind of basic foundational principles, which is what we'll try to do. Because of the nature of this course, we're going to stick, to small bits of this broader world. But just to know, like, this world's out there. There are a lot of cool things. A lot of cool places that you can take this. Okay. So, all right. Crossed out everybody's name. Okay. So we'll start with a definition. What is thermodynamics? I just showed you a whole bunch of things. We've said the word a whole bunch of times, just so that we all know what we're talking about. And this is the kind of definition that probably is useful today, and then by next week you'll know it, and you'll be sad that you wrote it down and wasted the paper. So I guess write this down if you want. So the definition is the study of energy flow and conversion. Okay. So it's these two distinct parts, and some of it overlaps with other maybe sub-disciplines, because that's how the real world works. But it's kind of these two different things. It's energy, and we'll discuss a little bit more. What do we mean about energy? But it's how does it move, and how does it change from one form to another? And we obviously come across this all the time, every day, right? You have a toaster. You're converting electrical energy into heat. You have a car. You're converting heat energy, chemical energy into thermal energy, because you're burning your gasoline, and then you're converting that thermal energy into motion or into work. Right? So we're running against these types of energy conversion processes all of the time, every day, all around us. An earthquake, you're converting potential energy into kinetic energy and then into thermal energy eventually. So all of these things, all of these types of energy transformation processes, these all fall under the broad umbrella of thermodynamics. There are really three parts that are kind of connected to this. The first part is conversion. So the conversion, how do you take one kind of energy and turn it into a different kind of energy that you want? Right, at least typically as engineers, we're talking about taking some type of energy that we have and changing it into another type of energy that we want. So the study of that process will deal quite a bit with that. Kind of a consequence of doing what we're going to be doing, we have to understand material physical properties. So energy is carried by and through materials, substances, air, water, the table, all of those things. So energy moves through those. So we have to understand a little bit about how those things actually work. That's where we'll start with a little bit today, is looking at material physical properties. We'll kind of look at a snippet today. And then the last part which is a whole branch of thermodynamics that we're not going to be studying today, but you might have seen in a chemistry course. Certainly if you are a chemical engineer and you take physical chemistry later, you'll see this one a lot. So when energy isn't flowing. So when it is moving, when it's converting, we have to learn about the materials, but then also things like when nothing is happening, when energy isn't converting. And we typically call that, the word that you've heard, is equilibrium. We mostly will live here. So there's kind of this whole area of things that we're not really going to touch on. But you may have seen you may have seen other places, you may still see other places if you haven't yet. Okay. So that's kind of a snapshot of what thermodynamics is more broadly. As I said, it connects to tons of different areas and sub areas, and there are lots of different ways that you can use some of these same things to think about interesting problems. But we're going to start today with a simple, and bear with me, it's painfully simple, at least at first. But just play along and answer the question, even if it's painfully obvious. So we're going to start with a thought experiment. And from this thought experiment, we are going to intuit, because we're not really going to prove, we're not going to derive, but we're going to just come to an agreement that, yes, these are like the foundational assumptions that we make about the world. Because this is where we build off of our other knowledge, is we make kind of like these base foundational assumptions that, like, yeah, this is just how the world works. And then we can take those and extend them and build onto them. And we're going to do that by a simple thought experiment and try to evaluate what are the assumptions that you made to come to the answer that you did. So, okay, so we have two containers. Right, these have water in them. Right, so we have two containers, each with a kilogram of water in them. Very exciting. I thought about doing this as a demo. Maybe I will someday. It would be a super exciting demo. So we're going to take these and we're going to mix them into a different container. So we'll draw a really big one. Right there, I just made an assumption about how the world works. I added 1 kilogram and 1 kilogram and got 2 kilograms. How do I know that if I have 1 kilogram of water and 1 kilogram of water and I mix them, I have now 2 kilograms? Conservation of mass. So even there, I've made kind of an assumption about how the world works. It's true, but okay. So my 1 kilogram of water, my first one, is at a certain temperature. So this is at, I don't know, 10 degrees Celsius. Okay. My second kilogram of water is at 90 degrees Celsius. What is my temperature after I mix them? Play along and answer the question. It's easy. Let it be easy. What's the final temperature? Pardon? 80. So it's certainly going to be between the two. It's going to be, so not 90 minus 10. It's going to be like the average of the two, right? So you're going to have, some amount, equal amounts of hot and cold, and it's going to be just the straight average. So 90 plus 10 divided by 2, it will be 50. All right, thank you. So 50 degrees, does that seem, can we all get on board with that? That that's what would happen? Okay. So let's explain, I guess, in words what would have happened. Well, let's do another thought experiment, and I'll do this one quick. So what if we had, say, 2 kilograms here and so I mix 2 kilograms of hot, or I guess 2 kilograms of cold, we'll say. Okay, is this going to be more warmer or colder than 50? It's obviously going to be colder because we have more cold water. And if we wanted to figure out what the temperature was, instead of a straight average, 90 plus 10 divided by 2, we would take a weighted average. 1 times 90, so this would be, say, 2 times 10 degrees C. 2 kilograms times 10 degrees C plus 1 kilogram times 90 C divided by 3 kilograms. And hopefully you can see that's basically, that's the same math that we did before. We just now introduced a weighting based on the mass. We could use that to figure out what the final temperature is. That's what 110 divided by 3 is 37. I don't know, that's not right. 36, 30, 38, something. It's a number. Maybe, yeah, like 38. Maybe. Low confidence in that number. Okay, so what we can say about how the world works, if we all agree this is how it would work. So we'll get a little bit more precise with some of our definitions, because in everyday life we're not always great. Sometimes we mix up heat and temperature, and I'm sure some of you will mix up heat and temperature. Those aren't exactly interchangeable. The temperature of something is the temperature, it's related to actually equilibrium. The heat of something is related to how much energy it has. So temperature, heat, not exactly the same thing. But what we can say about this system is, right, the cold water had to get hotter and the hot water had to get colder. And if we agree, like, this is how it worked, so this is the easiest one to see it. So the cold water went from 10 up to 50, so it increased by 40 Celsius. It increased in temperature. And the hot water went from 90 down to 50, it decreased by 40. So we increased one by 40 and decreased the other by 40. So a way that we can think about that is that the heat lost by the hot water again, we don't really know what heat is, but that's fine. So that is equal to the heat gained by the cold water. Okay. So that's one thing. But kind of from this second example down here, we would still say that that statement holds true. The amount of heat gained by the cold water is equal to the amount of heat lost by the hot water. Like the cold water gets hotter, the hot water gets colder. Those two things are equal. But we end up at not just the straight average temperature because we have different amounts of each. So the second thing that we can write is that the amount of heat is proportional to mass and change in temperature. Okay, so going, so if we have twice as much stuff, we have twice as much heat. And if we change like twice as much in temperature, that's going to be twice as much heat. So how much we changed in temperature, a change in 40 degrees Celsius is twice as much heat as a change in 20 degrees Celsius. We'll go back and kind of revisit these things because not everything is 100% true, such as life. But amount of heat is proportional to mass and the change in temperature. Okay. So these two things, I would argue, are true. They're kind of things that we just, maybe you haven't ever thought about in any depth. But I think looking at it, and you can kind of at least nod your head and say, yeah, that seems right. So let's do another thought experiment. So we have now one kilogram of copper and 1 kilogram of water. We're going to put these together, and it's going to look something like that. We're still going to we're going to end up with 2 kilograms of stuff. Let's say our copper is at 10 degrees Celsius, or our copper is at, we'll say the copper is at 90. And because that's what I have worked out. And this is at 10 degrees Celsius. Okay. What is the final temperature of our system after we let them come to this equilibrium, come to the same temperature? Okay, so when we had equal parts water and we put them together, we ended up with a straight average of 50 degrees Celsius. Now we have equal parts of 2 different materials. Would we expect it, you guys have to raise your hand, so would you expect it to be exactly 50 degrees still? Anybody? It's still just the straight average, 10 and 90, not 50 degrees still. Would you expect it to be higher than 50 degrees now? So we put the metal in, the metal's hot, we're putting it in cold water. Is that going to heat it up above the average temperature? Raise your hand. Do we have any hands? Any takers? Okay, some takers. It's reasonable. Would it be, okay, so for the rest of you, it's less than 50 degrees. Okay. I would like somebody, let's get 3 guesses, posit a temperature. So I'm going to pick your favorite temperature. What would the final temperature be? Yeah, Sam.
I'll give it like 20.
20. Okay. So it's way, way different than 50. So it hardly heated it up at all. Is anybody on board with that? For those of you that said it would be hotter than 50, what would be like a reasonable temperature? So like 51? Is it 80? 60? I don't know. Like 45? What would be a reasonable temperature? You are expected not to know this, okay? 70? Does that seem reasonable for the above 50, maybe 70? Does 20 seem too low? Seeing nods. What would be, so Kyria, what would be kind of your ballpark figure? Okay, 35, maybe like a little bit closer to 50. The real answer is about 17, so not even 20. So one of the things that we'll come across, and we'll come across this quite a bit, is, again, this is where heat and temperature are different things, and where sometimes our intuition is not great, because it's not great, because we haven't done things like this before. So I would still argue, and I would be correct in arguing, that both of these things here are true. So we did this experiment here. It is still the case. The cold thing, the water, went from 10 up to 17. It only changed by 7 degrees. Okay, not a lot. The hot thing changed by, what is that, 73 degrees. 10 times as much. It is still true that the heat lost by the hot copper was gained by the cold water, and those two amounts of heat are the same. Despite the fact that like the temperature change was way different, the heat energy lost by the metal was the exact same as that gained by the water. So there's one other thing that we have to think about, and that is that heat so we'll say it depends, well, not depends, it is proportional let's not quote it. Heat is proportional to mass. So if we had like 2 kilograms of copper, there's going to be twice as much energy there. So it's proportional to mass. Delta changes in temperature. So a change in 7 degrees C for the water is half as much as 14 degrees. So it's still, that's true. But then it also depends on, and it can depend very strongly on what your stuff is, what your material is. Okay, so that's kind of like a rough definition of heat. What is heat, and how is it different than just straight temperature? They're disconnected. They have obviously something in common, like changes in heat and changes in temperature are related. They're proportional to one another. But heat also depends on how much you have, and it depends on what you have. If you have water at 90 degrees, you have more heat than if you have copper at 90 degrees. Because the materials are different, so they behave differently. And that's where we're going to start diving in a little bit more to material properties. We'll revisit some of this stuff like the last number of weeks of the semester, the last like 5 weeks or something. So we'll come back to this, we'll flesh it out, we'll give more like, not just this qualitative hand-waving kind of language, but just at the outset to say heat and temperature are not the same thing. So heat is a an important thing that we're going to be talking about a lot: thermal energy, the energy of heat. We also, from these kind of simple experiments, we had assumptions about how things worked, kind of baked into our understanding of just, I mean, if we did it, this is how it would work. But there are some things that even though you didn't know, say, like for this example, you didn't know that the final answer was going to be 17, maybe you thought it would be 65, maybe 35. Those were all reasonable. What wouldn't have been reasonable would be to say it's going to be 120. Right? Nobody guessed that. I'm very glad. What wouldn't have been reasonable would be to say it's, well, yeah, so one is 90 degrees C, one is 10 degrees C. The final temperature is going to be negative 36. Like that, you know that that's not true. If I told you that was true, you would walk out because I'm lying to you. Okay. So what are kind of basic assumptions? Another thing, you didn't guess this at all. Nobody guessed this. I'm very glad, because you know how the world works. You know that you take this thing, the 90 degrees C copper, 10 degrees C water, you mix them together, and what happens is now the copper is 120 degrees and the water is 0 degrees. Right? That's not how things work. You take a hot thing and you mix it with a cold thing and they reach a middle temperature. Okay, so what are ways that we can put language around that? So those are the laws of thermodynamics. That's how things work. So the first one, the laws there are two laws in thermodynamics. They're kind of the assumptions that we were working with above. The first law is where we'll start in this class. The first law tells us that, well, really, it's a restatement of this, that the heat lost by the hot water is gained by the cold water. That we didn't like magically get more heat energy from something, like that didn't just appear. We didn't magically like lose it. It doesn't just go away. It doesn't disappear. It can move from one thing to another, but it stays the same total amount. So the first law, conservation of heat. Okay, that it's really, we're going to extend this. And really say that that's true more broadly of energy. That energy is not a thing that's created or destroyed. It's like conservation of mass. You don't like just get to say 2 kilograms plus 1 kilogram equals 2.5 kilograms. Like 2 plus 1 equals 3. Same thing with heat. So you don't get to like magically appear energy out of nowhere. That doesn't happen. You can change from one kind to a different kind, but the amount that you have is the same. Conservation of heat, really conservation of energy. The second law, and this is what has protected you from very outlandish statements about the previous things. And this is one that's, just kind of a built-in assumption that we have about the world because we know how it works because you've lived here for quite a while and you've never experienced the contrary, so you just assume, yeah, that doesn't happen. So the second law, heat flows from hot to cold. It flows hot to cold. It does not flow cold to hot. It is not possible to, like, you know, take an ice cube and put it on the counter, and the ice cube, or take like a cup of water and put it on the stove, and like the stove gets hotter and the water freezes. Like the heat doesn't go the wrong way. If you put water in a pan and put it on your stove, it boils. It gets hotter. It doesn't get colder and freeze, because that's not how the world works. That's something that obviously is painfully obvious, but some of the consequences, when you really try to dig deeper into that second law, especially, and start to put like math around that, it's going to be one that's will actually lead to stuff that's not so intuitive. And that's going to be something that we'll probably break it on accident and not really realize that we're breaking it, and then have to go back and say, oh, that we broke the second law of thermodynamics because basically heat was flowing from cold to hot, which obviously can't happen. So this is one. The second law is kind of the first law is easier. The second law is a little bit fuzzier, despite the fact that it seems like so painfully obvious right now. And we'll dig into a little bit more what that is and why that is the way that it is. So just another statement of these laws. So 1854. So just to get a sense of how people were talking about this stuff back in the day when they were first starting to think about this. Heat can never pass from a colder to a warmer body So I don't agree with that actually, because that's not totally true, because that can happen, right? So we can move heat from a colder place to a warmer place, like it's called air conditioning. And they recognize that already like way back in the day. So there are ways to make a cold thing colder and a hot thing hotter. Right, so you can make the cold place colder. We do that all the time. It's happening in this room, air conditioning. But you can't without some other change connected, one of my favorite words, connected therewith occurring at the same time. Okay, so what is that saying? So heat can't flow from the colder space to the warmer space. It can't flow from inside of your refrigerator to outside of your refrigerator into your kitchen without the refrigerator being plugged in. It's essentially what that's happening. Like something has to be happening in order to force it to happen. Okay, and we'll investigate a little bit more how that goes, but those are our two kind of fundamental insights, and those are what really lead to all of this fun stuff. So that's one of the things I like about science and about engineering is very basic. If you can put a framework around even pretty basic assumptions, you can build on those and get to a lot of really interesting and sometimes things that are not so basic. Okay. All right, so let's, so we're done with the first day of class, so let's start day 2. Hooray. So we're gonna take like a 5-minute break because it's the end of the first day of class. So why don't you go and grab a drink, go to the bathroom. We'll start back at like 5 till. Does that sound good? Okay, so head out, grab a drink, just sit in your chair, scroll through Twitter or something. We'll start back in 5 minutes. Yes. Okay. Yeah. Okay.
So when I register, it says I don't have the prerequisites of the registrar's office.
Okay.
Told me that I asked you to.
Yeah.
Override.
If you send me an email,
Okay.
then I can send you an email that says, yes, this is perfect. And then you can just forward that to the registrar.
They said there was a form.
Okay, then I'll, okay.
to fill out.
Send me, well, let me just, I'll write a note, a sec. Can you remind me of your name?
MERUEI.
The,
LLE.
okay. And how do you pronounce your name? Mefei.
Yeah.
All right, perfect. Thank you. Okay. Yeah.
Yeah, I see. For static. Well, the whole session, there was like 7 minutes. Sorry.
Okay, so I think we're going to get started again with day 2. Good to see you all again. So we'll start day 2 with talking a little bit about the course and how this is going to work, and then we'll have some more, a little bit more like notes kind of stuff, and then we'll hopefully end with you guys actually doing some stuff. I don't know, try to mix it up a little bit. So the course itself, so one of the first things I want to highlight is the opportunities for the study sessions that are available for the course. There are 2 different kinds of study sessions, student-led and me-led. So there's 2 student-led ones are led by Liam and Mary. I think you guys will like both of them. They're both really great. I'm super excited that they're helping out with the course. They're going to be really good resources for you all. So they're going to be leading help sessions, study sessions from 7 to 9 p.m. Both Monday, which is spelled wrong, and Wednesday, which is spelled correctly. So Monday and Wednesday, you can go to the intro lab 134 and say hi to Mary, say hi to Liam, whoever happens to be there, and work on homework, ask questions, talk about baseball. I don't know if either of them like baseball, but they're great. They're going to be, I think, really good resources. I'm excited to have them helping out with the class. These are going to start not tomorrow, but they'll start like this coming Monday. So if you go tomorrow, nobody's going to be there, but you'll be able to meet Mary if you go on Monday. The other opportunity is you can kind of office hours or me-led study sessions. So I'm going to be in Vanderwerf 222, which is the, I don't know, sometimes we call it the fishbowl, like the study room that's right up there, right across from the CAD lab. Like kind of in the, there's the hallway around it, right before the engineering offices. So I'll be up there 2 times a week, Wednesday from 4 to 5 p.m. and 10 to 11:30 on Friday. So hopefully with those 2 times, they'll match up. I know those times aren't going to work for everybody. Hopefully they work for a lot of people and don't have classes at least the whole time during those 2 time blocks. If you do, or if you can't make it a week and you want to come talk to me, of course, email me. We'll set up a time to be able to meet. If you have a quick 10-minute question, we can meet virtually if you want to. We can meet in person if you want to. I'm happy to help schedule things with you. So come one of those times, shoot me an email. We'll chat a different time. Right. One of the things about learning is it works better if you do it with other people. So Hopefully these are ways where we can work through the class and learn together. The course itself, and I'm going to go to the course Moodle page. This was just live like last night, so you probably haven't been here before. The first thing I want to pull up is the syllabus, which is right here at the top. So the syllabus, the same information about help sessions is up here right at the top. My email and office. So my office, I got booted from the engineering group office, the engineering offices. So I'm over in Scott. So when you come and bug Dr. Peckins about, hey, where's Professor Christian? I'm over in Scott. Such is life. So don't come over here to find me. I'm over there. Shoot me an email. That's fine. The textbook, hopefully we're trying something new, so I'd appreciate at some point your feedback, especially if it's going very poorly. We've done the virtual, like online textbooks before. This is the first year that we've done, I forget what it's called, but like this version of the textbook, or this way to do it. So if you click this link here, that should directly take you to your to our textbook. The textbook itself, I think, is it's reasonably good. I dislike the order that they do things. So we're going to do things super duper out of order. And I apologize for that, at least a little bit, because it's going to make, if you just read cover to cover, that's not the way that we're covering things. What you will find in the syllabus is a schedule that tries to show like what we're covering and when it's happening versus where that's found in the textbook. So hopefully that helps alleviate some of those things. What I think my goals for this course, I hope you get some basic understanding of how some kind of interesting systems work, but then also how we can use an understanding of thermodynamics to approach problems and think about problems, and use conservation of energy to think about how systems work. Be able to look at a better understanding of materials and their properties, and then, as I said, like apply some of these things to the solution of actual problems. How can we use that to think about the design of, say, a power plant or a refrigeration system or a heat pump? How can we use thermodynamics? The grading scale. So what I try to do with the grading scale, so the percentages listed there are not set in stone, but they're guidelines, and they are kind of like the minimum threshold. So if you got a 93.5, you're going to get an A. If you got a 92, maybe you'll get an A, maybe you'll get an A minus. But you have to be above 93 to be assured an A. But I usually set the cutoffs kind of depending on kind of how things go through the semester. The grading is combined of homework, quizzes, a midterm, a final, and participation. So you get a little bit of a sense of what the participation is a little bit later today. We'll work on that. It's my attempt at basically short assignments that if you try at it, you'll get 100%, but they're like, this is fail here. And if you fail, then go ask for help before you start doing homework. Right. So what always makes me sad is we have opportunities for help in the class. When you like work on one of these in class or one of these participation assignments, that's supposed to be your check for, like, if this isn't making sense before I embark on the next step, this is where I should look for help. So we'll try to do a lot of these. There will be time in class to work on a lot of it. So you can talk to somebody next to you in the class. You can talk to me. So I can get a sense of where everybody's at, but then also this should be like a self-check where if I didn't understand what was going on here, maybe, this is a time that I should be reaching out to to somebody and make sure that I'm caught up before going and like spending 5 hours on the homework, not making progress. Right. So hopefully this is like fail early and understand, okay, I didn't get that right, or, I wasn't understanding what was happening. So let's make sure I understand it before I do the next thing. So hopefully if you stay kind of with us and if you stay caught up, those should be easy points to get, but hopefully they're helpful in keeping us kind of an understanding of where you're at. Homework will typically be assigned every week. So we have a homework that's assigned today that's due next week. Those should be turned in class next week. So I have, and we have stuff to help remind you of that. So those are due the next week in class. As with all engineering homework, like work together, that's great. Go to help sessions, work with TAs, all of those things are great. Copying answers are not great. That's not learning. So force yourself to figure out what's happening. Don't just write down what somebody else did. There are some formatting guidelines here for how to attack problems. The two big ones, the ones that I have bolded, work problems clearly in a step-by-step manner. That's in part for me and for people grading, but it's more for you. I can promise you, if you force yourself to write down every step, you will do better. You will do better. So write down every step. And then similar with this second one that's bolded, give units for all answers. If you do all of your work and then put units at the end, you will be wrong lots of the time. Let your units help you out. A lot of times you can catch mistakes that you're going to make if you're like, none of these units are matching up and canceling out, and they're giving like joules to the third kilogram squared seconds to the 1/2. Like, you did something wrong. Here's like the tip, right? The units are telling you that something's not working out right. So show your work clearly, go work step by step. That's true on the homework. That's where you can practice and kind of get in the habit of it. So that it just happens on the exam. And if you show your work step by step on the exam, then I can give you partial credit because I know what you're doing and what you're thinking. Whereas if you're like skipping steps or if you're skipping units, I can't follow along, and then it's harder for me to give you partial credit. Right? One of the things that, like, my goal is that all of you guys do well. And I want to help you do well. One of the ways that I think that you can help yourself is working clearly, go step by step. It will be quizzes a lot of the time. Sam?
Is copy your paper acceptable for homework?
Yeah, I don't have specific paper guidelines. I should say that. Thank you. So yeah, not like ripped out of a 3-ring binder with like the hair going everywhere, but so like real paper. That's neat, but I don't particularly care what type of paper it is. So yeah, use blank piece of white paper, use lined paper, use engineering paper. That doesn't bother me. Yeah, good question. Thank you. So there will be quizzes a lot of the time. They will be short. There will be a quiz next week, so we got to start out the right way. Have no fear. It'll be pretty straightforward. In part, that should, hopefully we have one midterm exam and then one final. So hopefully the quizzes give us a chance to kind of make sure we're staying with things and staying caught up, and again, kind of a lower pressure opportunity to see, yeah, I really know this stuff, or oh, I didn't actually know that well. So that's kind of the goal for that. Yeah, other than that, for attendance, I'm not planning on recording every lecture. If you are going to be missing lecture, reach out to me. And then if you're going to be missing lecture and it's not like, hey, I'm going on vacation in the middle of the semester, like I can help out and I can record lecture for you. and make that available to you. But just reach out to me beforehand, let me know, we can make that available. If it like is last minute and you wake up Tuesday morning and you're throwing up and you don't come to class and let me know, I can record one of the Thursday lectures and get that to you. So just let me know, keep me in the loop, and we can try to work with that. The last thing to make sure to really highlight, I think just go through. Please go through in a little bit more detail. But the thing that would be useful to print out and just like put in your notebook or put somewhere is the course schedule. So this is where I try to say what we're going to be covering and where it's found in the book and big dates that are happening. So October 26th, we're going to be having a midterm. If you want to put that on your calendar, go ahead. That's when a midterm is going to be. The topics and sections are not 100% set in stone, so those are subject to change, but we should follow it relatively closely. So if you want to learn about what we're talking about today, really section 2.4, a little bit of some of the conservation of energy stuff in chapter 4, but we're going to get more into that next week. So if you look at the stuff on the right, you can see obviously we're jumping around a lot. We're starting in like chapter 2, 4, 7, then back to 5, then up to 9, then way back to chapter 3, then to chapter 10. So this hopefully gives you a sense of where we are in the course. The book is actually pretty good. It's not like a great novel that you should read every word and be hanging on every word. So use it like a textbook. But like go through, look at the example problems, read through parts of it. It is useful, it is helpful, but we do jump around a lot. The other date to put on your calendar is the final exam, December 14. That's a Tuesday, 12:30 till 2:30. So those are, if you want to put dates on your calendar, those are good ones to do. And obviously the syllabus lives on the Moodle page, so you can click on that and do that as well. How I organize my Moodle page, and I don't know, the feedback that I've got is largely positive, so hopefully this is helpful. I organize it by week. So you can see week 1, everything that you might want to have for week 1 is under the week 1 section. Everything that you might want to have on week 2 is going to be under week 2. And I'll arrange it so that whatever the week that we're currently on is at the top of the page. So week 2 will be at the top of the page next week, and then, I mean, you get it. So there are also some. So there are thermodynamic tables. I just gave you one. We'll talk a little bit about what those actually are. But there are just a number. These are also in the back of your book, but I understand with an ebook, it's a pain in the butt to find where they are because you can't just flip through them. So you'll use them for some homeworks, especially at the beginning of class. So if you have a question about ammonia, you can just come here and click on that and it'll pull up that section of the table. It should be a little bit easier to flip back and forth than using your book all the time. Because I know flipping back and forth in an ebook is the worst thing in the whole world. So hopefully that makes that a little bit easier. So for week one, I have it arranged that there's like a checklist of things that you should be doing in the class. I know we meet like once a week, so it's easy to get kind of disconnected and lost and forget what we did last week. So there's a checklist that if you just go through and like mental checklist, did I do these things? Yes, I'm good to go. And this is kind of the order that I would do them in. There's maybe a little bit more here than what maybe there will be every week. Not all of it is particularly time consuming, but just like go over and if you catch up with this checklist, you're good to go for the class, you're ready for next week. So some of this stuff we'll do, like some of you already wrote down help session out, like obviously some of this stuff isn't graded, but just a reminder to do that. And then homework 1, quiz 1, those are the things that are actually due next week, as well as in class 1, which we're gonna hopefully finish or basically finish except for maybe 5 minutes. We'll do that here in class. Okay. So homework 1, in class 1, and I'll try to like post everything that should all be up here. Hopefully it works pretty smoothly. But obviously if you run into any problems, just shoot me an email, let me know. Okay. So, yeah, so for next week, we will have a quiz. For this quiz, at least I have example problems. So these are some example problems. The quiz will have one problem like one of these. So these are just some things to kind of help you understand like what might it look like. There are two, so there's some kind of knowledge that I'm assuming that you have that you may not have. One is linear interpolation. We're going to use that a lot. Maybe you've never heard those words before. I just passed out tables like this. So the idea behind this table is to give you, and we're going to use these a lot, which is why I gave you a hard copy. This is the thermodynamic properties of water. So as he said, like every material behaves differently, each substance behaves differently. This is all of the data obtained from both experiment and modeling for how water behaves. You can think of it like this is the way that we would typically picture this, like a phase diagram. This is a phase diagram in numbers, in table form instead of in picture form. So this is those other thermodynamic property tables. Those are the same thing, a phase diagram, but in like number form. Because there are like certain values and not others, sometimes you need a value that's not actually on this table. It's like between two. So in that case, we're going to estimate where the value that we actually want is by doing linear interpolation, by basically like saying, you know, where is it in between these two numbers? If you need a refresher on how to do that, this is the equation that you maybe saw in conservation principles. But then also I think it's like a 10-minute video that explains and draws pictures and hopefully will help you figure out, okay, how do I do linear interpolation? So that's one extra video that might be worth kind of a refresher. Either now or even later in the semester, you go back and say, I always screw that up, like, let me watch this again. The other video, so this is the steam tables. I'm going to explain a little bit on how we use these and how we read these. But again, you may want a refresher because we're going to do a lot with reading steam tables. And if like that has to be second nature, basically, you know, after a couple of weeks, because otherwise you're going to be messing up problems that are more complicated because like we didn't get this, you know, this skill down pat. So there's an extra video on reading steam tables that kind of goes along with I have like an outline. So in the video, I have like this pulled up and I'm basically talking and drawing on it. So you can print this. I would say print out the first page. The pages after that are just steam tables. So I'll probably change that. But you can print this page out and then you don't have to write quite as much if you don't want to. But if you have that printed and then you go watch the video, that will help you fill in. And again, that might be useful this week. That's going to be useful for kind of review for the quiz, but that may also be useful like week 4. Like, let me just go back and look at it again because that's something I don't have second nature yet. So that's why I made those in videos. So hopefully you can kind of use those as references later if you need to. Okay. So these steam tables The steam tables that you have, let's just like flip through briefly and see what's there. So it starts, there are 4 kind of different sections of this. You should have seen, you did see steam tables before in conservation principles. So hopefully this isn't like totally brand new, but I understand we all like flushed the brain over the summer. So there are like 4 sections of these. The first 2 sections are, right, it kind of says right up here at the top. So it says at the very top, thermodynamic properties of water. So that's the substance, water. This table, B.1.1 is for saturated water, and then it has all kinds of information. Temperature, pressure, this thing, specific volume, and then it has things like internal energy, we haven't talked about yet, enthalpy, entropy. So there's some more here than what we talked about so far, and what we'll talk about this week. But there's a lot of numbers. So if we go, now we got to the next one. So that was all table 1.1 here at the top, the first couple pages. And then it flips to table 1.2. And then there are a couple pages of that. That still says saturated water. Then it switches to table 1.3. And then it changes a little bit. It looks a little bit different. Now it says superheated water vapor. Superheated water vapor, that's going to be kind of the fancy technical term we use for just like a gas. The gas, the normal gas. It's water behaving as a gas, so it's steam. But it's just being a gas. Like the air in this room is superheated nitrogen, mainly. That's differentiating it from saturated, which is something we'll talk about in a second. So if your water is a gas and it's behaving as a gas, this is where you'll find it. And then at the very end, so we have a couple more pages of that, a couple more pages. There we go. Then here at the end, we have table B.1.4 for compressed liquid water, which is again kind of a weird term, but it means just a liquid. Like water sitting in a cup on the table that is compressed liquid water. It would be our technical term for it. It's liquid. It's a normal liquid. Okay. So these tables can help us to understand the properties of substances at all kinds of different conditions. So you see like tons of different pressures and temperatures. So that's temperature. Tons of different conditions. We can see like how is that substance behaving? Is it a liquid? Is it a gas? What are its properties? How much heat energy does it have? We'll see other things too. What's its volume? How is it behaving? What does it look like? So that's kind of what we can do with these tables. We'll ask a couple questions in a minute and get some practice, like how do we actually use these? But before we do that, I want to jump over to these notes. So the second thing we handed out today is like a page and a half of notes that I think will help us kind of keep some of this stuff organized. So we've learned about phase diagrams before, but just a couple quick reminders on what that is and how that looks. There are 2 different pictures of phase diagrams. We're going to deal with a lot of different types of phase diagrams. What we mean by a phase diagram is just like what we're graphing one property against another property and saying kind of how does the material behave. So if you think of, so I have a syringe here. It has liquid water in it. It's water at, I don't know, whatever room temperature is, 21 degrees. If I pull the plunger, right now I have, you can see all the bubbles that are forming on the side. I'll let you guys do this in a second. But you can see the bubbles that are forming. Those bubbles are not air. That's boiling water. Right? It's still obviously the same temperature, but it's the water is boiling. It's boiling because I reduced the pressure or increased the volume. So I reduced the pressure by pulling my little plunger, and then the water boiled. So we can understand questions like, you know, how does this work? What conditions is, like, what pressure does it take for the water to actually turn from a liquid into a gas? How does that happen? We can use our thermodynamic property tables to answer those questions. We can think about that in terms of a phase diagram like this. So for example, let's label a couple parts of our phase diagram. So if we look first at the one on the left, we'll label all of these, or as many of these different things as we can. So over here would be, well, I'll label it, that's going to be our solid. Up here, this is compressed liquid. I'm using the little variable f, which is a dumb variable, but that's what our book likes for compressed, for liquids, use f. So maybe fluid, I don't know, but gases are fluids too, so that's dumb. So I don't know why they use it, but we'll use it to make them happy so that we don't get confused later. So that would be solid, that's liquid, and here is gas. So, right, so this is kind of our basic phase diagram. If we're thinking about this system here where I have this syringe, where I am right now is actually, I'm not a liquid or a gas, I'm both. So down here, I'm a liquid, I'm liquid water. Up here, I'm water vapor. So I'm both. So this would be a system that we call saturated, because it's a mixture in equilibrium. It's both liquid and gas existing together, right? Just so that's going to be that line is saturated. So if you think of you don't have to draw this, but the experiment that I'm doing here, when the water is just sitting here and I'm not pulling on it, I'm like right here. And then as I pull on the syringe, I'm pulling, nothing's happening. And then eventually I start to actually move the syringe. Then I'm on this line. So I'm decreasing the pressure until I bump into that line. And then it doesn't get harder to pull. It's the same difficulty to pull because I'm stuck at a constant pressure, just increasing the volume, just increasing the proportion of liquid versus vapor. Okay. So a couple other points on our phase diagram. Up here is the critical point. Liquids and gases are the same at the critical point, and we'll talk about that later. just, it's a magical thing. Down here is, we call the triple point, where it's possible to have a boiling cup of ice water at the triple point, which is a very exciting thing to think about. So you literally have a cup of ice water that is also boiling. So you can have all three phases all in equilibrium at the same time. Okay. And then saturated liquid, saturated vapor. A saturated liquid, yikes. Saturated liquid is liquid just about to boil. A saturated vapor is a vapor that's just about to condense. So you can think of it's like your pot of water, when the first bubble forms, that's a saturated liquid. A saturated vapor is the vapor with like the first droplet starts to condense. So it's all vapor, it's a gas, but it's just at the boiling point or just at the condensation point. A vapor liquid mixture is mix of so it's the mixture that is currently boiling or it's like partially boiled. So like when I pull this down here, I think I broke it. That's sad. I'll have to fix my seal. But when I pull this down here, then I have a mixture of like liquid water and vapor water. I'm a saturated vapor liquid mixture. Some of my liquid is boiled, some of the, okay. So this is kind of the normal phase diagram that we would look at. This whole line here is what we would normally think of as like, that's the boiling point. So if you cross that line, you go from a liquid to a gas. If you're on the line, you are in some state of boiling, but you can't distinguish like, okay, so you're boiling, but are you mostly liquid? Are you like half and half? Are you mostly vapor? Are you all vapor? Like, I don't know. So often we'll draw the phase diagram a little bit different, like the graph on the right, because that can help us distinguish like four things that are actively undergoing a phase change. Where are we? So for here, up here is the critical point. So instead of graphing pressure and temperature, we're graphing pressure and volume. So obviously liquids and gases take up different amounts of space. So if you boil something, it expands. So gases have take up more space. So out here, out here, you're going to be a gas. Over here, you're going to be a liquid. Right? Liquids don't take up a whole lot of space. Gases take up a lot of space. They have a higher volume. This here is saturated liquid. This here is saturated vapor. Some of these things are not shown, like solid is not shown on this graph. We're typically not interested in solids in the context of this class. That's something, obviously, thermodynamics, sure, but in this class, not so much. And here we would be like vapor / liquid. So under the curve were some mixture of vapor and liquid. to define or specify where you are on this graph, you need, I mean, maybe it's clear from the graph, you need to know your X and your Y position, and then that can tell you where you are on the graph. So to be able to figure out where you are in a phase diagram, you need to know two independent thermodynamic properties or thermal properties. So what are some examples of these? Like temp, pressure, specific volume, and then there are a whole bunch of other ones too. So I'll just write some, we'll write some variables, U, H, S. Okay, you don't know what those are yet, it's fine. The caveat about saturated substances, so if I know that something is boiling, and I know the temperature and the pressure, that's fine, but that's not actually, those aren't independent. So if I know something is boiling, and I tell you that it's 100 degrees Celsius, you know that it's atmosphere. If I tell you the water is boiling and it's 100 degrees Celsius, you know that it's atmospheric pressure. Because pressure and temperature are linked in a boiling substance. So temperature and pressure are not independent if something is saturated or if it's boiling. So temperature and pressure are not necessarily independent all the time. So if I tell you like, so this is liquid water, it's at 20 degrees and atmospheric pressure. Temperature and pressure are independent. It tells you everything that you need to know all of the properties of this water. But if I, if I pull my plunger and my water starts to boil, now that's not the case because you know it's 20 degrees and it's boiling. So that tells you exactly what the pressure must be. It can't be anything else because it's boiling. So a little bit of a caveat. So we're going to stop there. We'll finish the rest of these notes next time. What we're going to do is spend a little bit of time playing with, playing is the wrong word, but it should be fun. Playing with this class number one. So the goal of this is just to spend a little bit of time using our thermodynamic table. So we have like 10 minutes. It's a little bit less time than I wish we had. But I think it should be enough time. Again, this shouldn't be totally new, hopefully. If you find yourself struggling with this, I would ask you to go and watch the video on how to read the tables first. This is essentially like questions like this is what our quiz is going to be on. So hopefully this first week we can kind of remind ourselves what we did in conservation principles, how we can read thermodynamic property tables like this. We'll spend a little bit more time next week talking about some more details of it, but yeah. So pull this out. This will be due next week. You can obviously like work with a friend, spend the next 10 minutes talking to me, ask questions. I'll be walking around the classroom. So ready, begin.